Hey everybody, it's Eugene here and welcome to another Recon-3D video. This one is going to be another accuracy study and I'm going to be going over what we did in a recent publication that was in the Association of Crime Scene Reconstruction. This is one where we gathered a whole bunch of data from a number of different people who are on our training course, and we just made all the data available so that people can see for themselves what kind of accuracy you can get out of the Recon-3D app. Now, not too long ago, I released another video, and that was a video of Jared Carter from Origin Forensics, who presented a study that he did at our user group meeting. And it's not a published study, but it's something that he did put in quite a good effort in. And I thought it would be interesting to release that video because the results were just quite informative. Now, this one is a different one because this one uses point-to-point measurements solely. And in the previous video, I talked about accuracy being sort of having different perspectives, okay? So there are different ways to measure accuracy depending on what it is that you're doing. So for example, when you're scanning with the app, you could say that, measuring by hand, point to point will give you, decent accuracy, or maybe that's an activity that you do regularly, so you're most interested in that. On the other hand, you could look at something like Cloud Compare that will do a 3D analysis or a point-to-point or distance-to-distance analysis on two different point clouds. And that gives you a kind of heat map, or it gives you the relative distances between two different point clouds, and you can see where there are defects, where things are better or worse. So that is another way of looking at accuracy. Part of the reason for this is because there's just so many different ways to look at accuracy and where errors can come from. So there's the sensor itself, looking at the range and how you use the sensor. There's the environment, there's the object itself, and there's even the capture method, so that the way that you actually move around the object to capture the data will have an impact on what you get. So a number of different factors, but nonetheless, it's all about the totality of all of these different studies and papers. And so we here at Recon-3D are totally committed to trying to get as much information out there as possible. So this is a study that we published not too long ago. It was received in September 2022, but accepted on April 1st, 2023. This one was a study that looks at hand-to-hand measurements or point-to-point measurements, people mostly using a steel tape. So in our very first Recon-3D training course, I had all of the students do an exercise, and I'll talk about that exercise. So it's important to know that this is an uncontrolled test, meaning that, it wasn't like I was looking over people's shoulders. This is something that they worked on independently. So what I want to do is go through the study little by little and explain what the participants did, and then go in and talk about what the results were like. So let's start with what the participants actually did in this study. Okay, so the task at hand here was for the students taking the Recon-3D class to make a small scene, like a small crime scene or a small area that they wanted to measure. And so this could have been an indoor scene, it could have been an outdoor scene, it really didn't matter. But what was required was that they use the April tags inside of Recon-3D. Now, the April tags are two targets, and if you measure the center to center distance between those targets and enter the distance into the app before you scan, it basically makes a fine adjustment to the overall scale. So that was one requirement that they had to do. The second thing was that they needed to put up a number of targets, and that's these little triangular targets here, and they're numbered, okay? So you can get 10 of them and just spread them out. But the idea was to get 10 measurements across this room or this scene that was indoor or outdoors. Now, this was entirely up to the participants, so it didn't matter. Some people had, did their living rooms or their bedrooms. Some people did outdoor, driveways or other areas. There's a wide variety of scale, a wide variety of environments here. And that's okay. There's nothing wrong with that. So here what I'm doing is I'm showing an example where you have two of the April tags here, and there's a steel tape that's been run between the two, and that's what you'd like to do. And typically those April tags are going to be relatively far apart in relation to the scene or the other targets that you're going to be measuring. This is just another view here, and this is a close-up here of one of the targets. So they're basically two triangles that come together, and they're going to be putting up a whole bunch of these throughout the scene, and they're going to be measuring between them. Now, the reason for the two triangles pointing at each other is that it helps to give you a discrete location to measure from, and this way there's less subjectivity. So if you have, the corner of the room or the top of the door or something like that, that can be subjective. So we wanted to have at least a discrete location to measure from between these numbers. Once they did that and they have measured a number of things, or at least the distances, they're going to fill out a table. And this is just an example table where, you have 10 measurements and you may measure between, target 1 and 2 and 2 and 4 or 4 and 5, whatever it might be. But what I did ask for was, some small distances, some medium distances, and a few far distances. So, if you get up to about 10 meters or so, that would be great. It's relatively small scenes. And so, up to 10 meters is not very large, but, I was thinking of, a car, I was thinking of a room or something like that. You need to keep all that in perspective when we talk about this particular accuracy study, because it doesn't include things like long roadways or very large buildings. So yeah, definitely a smaller scale. Now, once they did all of this and they scanned it, then we took the data into Cloud Compare. So they basically process their scan data. It comes back with an E57 file. They open up the E57 file inside of Cloud Compare, and then they start taking measurements. So let me switch over to Cloud Compare, and I'll give you an example. Okay, so here we are in Cloud Compare, and this is an example room that I just show the students on how I'd like to see this setup. And this is just a simple example, but they're free to do a number of different setups or different areas or whatever. So first thing is that we have a couple of the April tags. So there's one there and there's one there, and this is where we're going to have some scaling. The second thing is that we have all of these targets that are spread out. And so what they need to do is they need to measure between, let's say this one is target 9 here, and then, this one's target 4. So for example, they would take a measurement between these two with a steel tape, but then they would come into Cloud Compare and they would take a similar measurement. So you can do that by using some of the point picking tools up here. And basically, if I click there and then I click over here, okay, I basically end up with a result. Okay, so this is telling me it's 2.083. So I would take that number and then going back to that table that we have, this guy over here, basically, is between 2 and 3, or I should say 9 and 4 in our case, but whatever the two targets are, they're free to put them here and then basically say, this is what the steel tape gave me for the known distance or the reference. And then this is what Cloud Compare, what the measurement was in Cloud Compare. And they put that down there. And then there's a table. It measures the error, the absolute error, the percent error, and the absolute error. Okay. So a number of different things. So let's talk about the results, and hopefully, some of that might be informative to you. Before I jump in, I guess I should say that you can get this study because it's basically freely available on the ACER website. So that's the Association for Crime Scene Reconstruction. And if you go to acsr.org, 2023-ACSR-journal, you basically end up here. So, or if you get to their main page, just go to the journal and then drop down 2023 ACER journal, and you can basically click on the study and download it as a PDF. So it's freely available. So this is the paper. I'm not going to go through the abstract. I'm just going to jump right in. A lot of this gives some background information to the LiDAR and things like that. And, in talking about accuracy, for example, here we have an example, sometimes with different apps or photogrammetry or different technologies, you see that you may get a result that looks okay, but when you shut off the textures and colors, right, you get a big mess. And so when we're talking about accuracy, it depends. It could be that in a case like this, if you were to measure from the front to the back of the vehicle, you might get a decent result. But if you look at some of the mesh and some of the quality of what's in between here, it could be an absolute disaster too. So it depends on what it is you're doing and what the application is and what the final product is going to be. Now, in our case, Recon-3D is obviously an app that is dedicated to, forensics, crime scene, crash scene, public safety. So we're really talking about raw data. And by that, I mean, the closest thing we can reconstruct is the point cloud. And then from there, if you create a textured mesh or whatever, that's sort of a subsequent operation. And so to me, point clouds don't lie. If there's noise, you'll see it. If there's missing data, you're going to see it. And when you create a mesh, there's different things that are happening there. So in some cases, you're trying to soften the noise. In some cases, the noise gets even worse and gaps get filled and data gets interpolated. So for me, it's more important to start with at least the point cloud data and know exactly what you have. So let's get on here, talk about a number of different things, but I'm going to jump in right to the results. And that looks like it's right here. So first thing, there were 60 participants that made up part of the course and who submitted the data. Now, I have to give a caveat here because in some cases, there were some very gross errors. And what I mean by that is people just made human errors, mistakes. And so, for example, over a distance of 10 meters or 5 meters or 6 meters, if you make a mistake that's 1.5 meters or a measurement error that's 1.5 meters, you would think that that would be noticeable. And in almost all of the cases, the people who made these errors just, it was an oversight, something they didn't understand, or they clicked on a point that wasn't actually the point that they wanted. It was something else, or it was, some kind of a scribing error or something like that. So fortunately, I had asked all the people to send me their projects. So I reviewed each one to make sure that all the measurements were okay. And in cases where I saw very, very large errors, then I would send that back and say, hey, look, I think you made a mistake. Just go back and check it out. That being said, this is the data set that came up. Now, we did allow for errors that were up to 10 centimeters. And the reason for that was some of them were still obvious, but just not to be too biased, we left them in there anyway. And so what I want to do here is have a look at some of the data. And let me just flip to some of the graphs here. Okay, here's some of the summative statistics here. You can see here when we have 60 people, so there was about 600 measurements. The average turned out to be about -2 millimeters. Okay, so that's taking into account positive and negative measurements. So if the measurement was smaller than what you originally measured with the steel tape, or if the measurement was larger, we take that positive or negative value into account for the average, and we end up with -2, which is good. That's what we want. You want to have some kind of a average that's around 0. Now, there's also the absolute error. So the absolute error is a worst case scenario, meaning that you're only looking at the magnitude of the error. You're looking at how big each of those errors were in each case. You're not looking for the plus or minus, because when you take the plus or minus, it basically averages out. So for example, if I have 10 measurements and the first 5 measurements are all -5 millimeters, and then the next 5 measurements are all +5 millimeters, the average of those would be 0. But in each case, I made an absolute, or if I were to look at the absolute errors or average, it would be 5 millimeters. So I made a mistake each time of 5 millimeters. So you have to be able to distinguish between the two. And so reporting the absolute error is the way to go. The percent error is 0.078, so -0.078. So it's very, very small. It's not even up on a percent. It's not even 0.1%. It's below that. But of course, that is, again, assuming the positive and negative. But if we take the percent absolute error, then we're at 0.4%. So we're at a very small number in terms of the overall measurements. Now let's scroll down here and look at a few graphs, and I'm just going to shrink this down a bit so everybody can see. So this is a distribution of the errors, and it's in millimeters. And if you look here, this is the 0 mark. And as we go up, this is what we want to see, right? We want to see that the frequency of errors around 0 was the greatest. And then as we go to 10, 20, 30, and 40 millimeters, they become very, very sparse. So the majority, okay, if you look at the majority of errors, they're going to be within 3 centimeters. So when you're measuring by hand, about 95% of the points or more are less than 3 centimeters. And that's good. And that's a good sign. But the majority, of course, you can see hover around the 0 mark. Great. Now, when we look at the absolute, okay, that has to increase, right? Because the absolute is not going to account for the negative or the positive. So in this case, when scanning with Recon-3D and taking point-to-point measurements, you can see here that we're starting to get about, when we look at the frequency, about 5 millimeters was the most common error, 10 millimeters next, 15, 20, 25, and 30 being much rarer. So again, this is pointing to that most errors are going to be less than 3 centimeters, with the majority, right here, being less than about a centimeter, 10 millimeters or so, which is good. Now we can move on and also talk about the percent error. And this can be useful. I mean, I like to talk about real numbers like in millimeters, but sometimes if you want to look at the overall, then percent might be interesting. And again, when we look at this, it's very similar to what we had with the previous or distribution. The frequency hovers around the 0 mark. And if you look, and again, this is percent. So if we go up to 1% error, that's somewhere out here, 1.5%, 1.75. So almost all the points are below 2%, but with the vast majority well below 1%. So even I would say, well below 0.5. And that's positive. That's what we want to see. Again, when we look at the absolute percentage, so we're not taking into account the positive and negative errors, then here, again, about the majority are below 50% right over here. But as you go up, if you really want to go and say, what's the totality of all of this? Well, definitely below 2%. Okay. And that's sort of looking at an extreme value, much less frequent here to get errors up, in that particular area. Now, we also looked at distance and, were measurements that were taken over 10 meters or 7 meters greater than the ones that were taken over, 3 or 4 meters or something like that. And when you look at this particular graph, we put them into little buckets. So for example, from 0 to 1 meters is over here, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and then anything greater than 6. And the reason for that was there were less measurements that were up at 10 meters or so. So in this regard here, you can see that the X here, or the line, I should say the main bar here in the middle of the box, that's going to show you pretty much what your averages are looking like. So you can see they hover around the 0 mark, and that's pretty good, except here. Okay, so when we start getting greater than 6, we start to get a little bit of a negative number here. So the average is below 0 and a little bit more than the others. Not greatly, but a little bit more. So it might tell us that, there's something going on here with greater numbers. But again, just looking at the graph, it's not completely obvious. You can see a little bit more variation as we get to, between, let's say, 2 and 5 meters, a little bit greater. We get these outliers here. And so that might be interesting for some people, but definitely on the low side, it's a lot tighter. And even here, I wish we had a few more data points, out at 10 meters or so. But again, there could be something going on here. But the point is, nothing really obvious here. Okay. Nothing too obvious. So, I think this requires a little bit more analysis and maybe a little bit more data, especially out at the, larger numbers here, larger distances. So that is a quick review of this particular paper. Like I said, you can go to the ACSR website. It's available. You just go to the journal and go down here. Also, if you want to go to the Recon-3D website, there is our tab here where it says research, and there are a few studies here. Okay. Another one that's available is the one by, let's see here, Soren Kotner. So using the iPhone's LiDAR technology. Maybe in the future, I'll do a quick review of that one with Soren as well. Another one that is available through the SAE is this one here by, Seth Miller. And that one is purchased. It's not, freely available or open source, but it is available for purchase. And that may be another one that I put online at some point, or maybe I'll get an interview with Seth and we can talk about that a little bit more. So folks, that's it for this one. Another accuracy study. In the coming months, there are going to be more papers that are going to be released looking at application-specific studies, like things like bloodstain pattern analysis, crushed vehicles, looking at things like bullet trajectories. And as those come out, I'll be sure to include them on the website, and I'll be sure to do a little video and a review of what those mean and what they mean to you. Thanks, everybody. Take care, and we'll see you soon. Bye-bye.